Hello and welcome back to episode 5 of Calculus 1. I'm Mohammad Momenzadeh and we have the continuation of the limit discussion. So in this lecture we will discuss about the remaining undetermined forms of a limit, and let us directly go to the points that we should talk about it. So let us take a look at the diagram of the limit. Here we have the diagram of the limits for the cases that we should talk about it. Previously we talked about the cases of 0 over 0 for the algebraic ratio and trigonometric function, and today we want to start our discussion by talking about the case of a number over 0. So let us take a look at one example, and over the example we will discuss about the situation. So over here, if you just take a look at this example, as I said it, when you want to calculate the limit of a function, the first step is substituting the value of a inside of the function. And if you just substitute it over here, we have 1 plus 1 plus 1, which is 3. So we have 3 over and if you just substitute 1 at the denominator, we have 3 over 0. Right now the case is not as the same as 0 over 0, that we have a 0 factor, and we can indeed, by substituting the value over there and factoring the 0 factors from the expression, you can simplify them and then evaluate the limit. So over here we have a number over 0. So in this case we should calculate the limit in two cases. One in a case that x tending to the 1 from a right side, and the another one is a case that x tending to the to that number, or over here 1 from a left side. And for each side you should decide about the sign of 0. Of course 0 has not a sign, but the things that we talk about it is about the value of 0, which the 0 is greater than 0 indeed at the limit, or the value of 0 over there is less than 0 at the limit. So what does it mean? It means that in this case we should split the situation to two limits, and for each of them you should calculate the given value. Over here we just rewrite the same limit over here, so let us rewrite it over here. And one times I just tend to 1 from the right side, so I put the plus at the top of the 1, means that we are tending to 1 from the right side, and the another time I tending to 1 from the left side. And in each case we should decide about the value of the limit. Indeed, if you just take a look at the limit, so let me just rewrite it again over here. At the denominator of that limit, which is important for us, we can split that x squared minus 1 to two parts, means that we can actually select this part and split it, or make it as a 2 factor. So if I just split it to 2 factor, then by conjugate identity we can rewrite it as x minus 1 times x plus 1. So if I substitute 1 and the value more than 1 over here, then we can see that this part is 2 indeed. This part is 2 or greater than 2, and the right side and the left side of this expression x minus 1, since x tending to 1 from the right side, is 0 plus. So you may put some value greater than 0 inside of the limit to decide about the sign of 0 as well. Over here, as you can see, where x is tending to 1 from the right side, means that x greater than 1, then the denominator of this fraction will be greater than 0. By the another word, I can rewrite this one as 3 over 0, but the sign of 0 over here is plus, means that it's greater than 0. As I said it, to make sure about your calculation, you may put some value greater than 1 instead of x, means that you can decide about the point where x is equal to, let me just mention it here, that x could be substituted by one value which is greater than 1, for instance 1.1. If you put 1.1 instead of the x at the denominator, as you can see, the value will be 0.41, and that value is greater than 0, so it's 0 plus. And the number over 0 always will be equal to infinity, but the sign of infinity is based on a sign of a number and 0. And because the number is positive and the sign and 0 at the denominator is positive, positive over positive will be plus infinity. But at the denominator, at the another case that we have it over here, means that for this case, as you can see, again, if we rewrite the expression over there, means that if we exactly write the same terms over here, so let me just rewrite it here. So if we just write the same terms, but this time instead of putting the x as a 1 plus, if we put 1 minus, means that the value will be less than 1, then the situation is change a bit. Means that in this case, if I just substitute that one by x minus, let me just put minus at the top of 1 to decide to determine that we are tending to 1 from the left side, then as you can see, the value of x plus 1 is equal to 2 is less than 2. It doesn't matter, it's not affect a lot of things. But for the case that we have the value less than 1 and we put it over there, we have 0 minus. Over here, minus minus will not be plus. Indeed, this 0 multiplied by 2 make it 0, but it's less than 0. For instance, for making sure, you can put for instance 0.9 over there, and if you put x equal to 0.9, which is a value less than 1, instead of the x, then it will be 0.81, the square of it, and if you subtract 1, the value will be negative. So by the another word, the denominator of this one will be 0 minus, or less than the 0, but the numerator is 3, and the plus number over minus will be minus, and the result should be infinity, so the result is minus infinity. In this case, because the right side limit and left side limit does not equal, so the limit does not exist, and we can denote it by D and E, means that over here the limit does not exist, and for this case we can say that the right side and left side limit are not as the same. However, the value is infinity. So at this case, as I said, it is important to decide about the sign of 0 and the sign of a number at the numerator. The next example is totally similar to the previous example that we solved it in a previous lecture, but over here we have tangent x, not tangent square of x at the numerator, and these small changes can make a lot of differences over here. So let us solve that one and decide about the situation that we have it. If you substitute the value over here, the actually undetermined form is as the same as 0 over 0. So we should solve it in a previous method that we learned. It means that we should apply the similar method that we had it previously. Let me just erase the first example and focus on this example over here. So if you just take a look at the situation over here, we have this limit and we want to solve it, and by substituting we realize that it's equal to 0 over 0. So we should apply some trigonometric identity to simplify that expression, and as you can see, we have 1 minus cosine x at the denominator, so the best thing is multiplying these terms by 1 plus cosine x, which is the conjugate of the denominator, means that we just multiply it by 1 plus cosine x and divide by the same term to avoid inequality. So we should have the same terms over here. By multiplying the denominator by that terms, then we have the following expression, means that this limit will be changed to this case. So at the numerator I multiplied by 1 plus cosine x, and at the denominator, because it's a conjugate of 1 minus cosine x, the result will be 1 minus cosine square of x at the denominator. The second one becomes a square, the first one a second one indeed. So, and 1 minus cosine square is sine square. So we can rewrite that limit as follow, means that it's gonna be limit of x tending to 0 up to here is as the same as previous things. So over here, instead of the denominator, you should write sine square of x. So it's good up to here, sine square of x. And instead of the numerator, we have tangent as a sine of x over cosine of x. So I substitute that tangent by sine over cosine of x, and the terms as 1 plus cosine x remained at the numerator. So let us eliminate or cancel the elements that make this fraction 0, but still we have one sign at the denominator. Means that if you just eliminate or just cancel the term sign, then the result can be rewritten as follow. Means that we reach to this type of the limit, after that we simplify it. So we have limit of x tending to 0, and at that fraction, let me just write the fraction, at the fraction that cosine x can come to the denominator, and then we have sine x and also cosine x at the denominator. So let me just write it over here, sine x and cosine x, but at the numerator we have 1 plus cosine of x. Right now, if again we substitute the value, then we will not have the 0 over 0. Indeed, right now the limit is changed to the case of 2 over 0. So this 1 plus cosine of 0, if you remember that it's 1, 1 plus 1 is equal to 2. So we have 2 over sine of 0 is equal to 0. So we have a number over 0. And as I said it, if you reach to the case of number over 0, you should decide about the limit by evaluating the right side and left side limit separately. So let us split the situation to two cases. One case, the case that we have the right side limit, and the another one for the left side limit. So it means that one times we should evaluate this limit. I rewrite it here for the case that x tending to 0 plus, and one times where x tending to 0 minus. So 1 minus 1 plus over here. So to decide about that one, it's not a bad idea to keep it in your mind that what is the situation in a trigonometric circle. You remember that we discussed about this trigonometric circle, and we said that the value of sine should be considered in a y values. So the y value determine the sine of x, and we name that axis as a sine axis, and the horizontal line over there determine the cosine axis, and the value of x at the end of that actually point determine the cosine of x. For instance, if I have this ray over here, which determine the angle of alpha over here, or x over here, so for instance x, then let me just name it by theta to avoid the problem with that case. So let us call it the theta. So if we have theta over there, then the endpoints of that ray has two components. One of them is x and one of them is y, and we said that this x actually determined by the cosine of theta, means that the first component determine cosine of theta and second component determine the sine of theta. So the endpoints of that one determine the value of cosine and sine. And as you can see over here, if we consider the actually ray over here, one ray over here, and we have the 0 plus, means that it's too close to 0 but it's greater than 0. So this value indeed over here, this value that we have it here is theta, and this theta is 0 plus, means that over here we have theta, and theta is 0 plus. And if the theta is 0 plus, as you can see, the x and y value, both of them are positive, means that both of this value sine and cosine at the denominator are positive. So we have 0 plus at the denominator, and at the numerator also we have 1 plus cosine of 0, and cosine of 0 is equal to 1, as you can see in the circle as well, and it becomes 2 over 0 plus, so the value over there will be plus infinity. And for the case that we have 1 plus cosine x over sine x cosine x and x tending to 0 minus, then the ray that we should consider it should be considered over here at the fourth quarter. Means that over here, as you remember that the clockwise direction determines the negative theta, so this theta over here determined by 0 minus. So if it's 0 minus, then the cosine will be positive, or the x value over here means that at this point the cosine or the x value is positive, but the y value or the value of the sine, which is determined over here by this segment, is negative. So this one is negative, and the cosine will be positive, and positive times negative will give us the 0 minus, and the 2 over 0 minus give you the minus infinity. So because of that, the limit does not exist, and in this case also we determine that the right side and left side limit are not the same. So it's not a bad idea to take a look at this function in a diagram and in two-dimensional space. So again, I just used the Desmos website to sketch the function. Simply you will write the function over here, y equal to tangent x over 1 minus cosine x, and you can see the situation over here. When you just tending to 0 from a right side, means that when you just tending to 0 from a right side, let me just make it smaller to see that what's happened. When you just tending to 0 from a right side, as you can see, as much as you be close to 0, the value of the function will be bigger and bigger. Means that by tending to 0 from a right side, the value of the function becomes bigger and bigger and tending to infinity. But at the left side of this function, when you tending to 0 from a left side, the value will be negative and minus infinity. We indeed we evaluate that type of the limits for the case that we had the tangent square of x. If we just square that one, then as you can see the value at the point 0 will be undefined, and we calculate that case as well, and we determine the value of the function at that point as well. But as you can see, it's tending to that case, means that it's tending to 0.2, so the limit will be 2 indeed at the point 0. So this is the case of this function, and you can see that type of the function over here. So now let us take a look at the diagram. The remaining part is a calculation of the limit at the infinity. It means that let us take a look at the next slide. It means that we want to calculate the limit of fx, limit of a given function. For instance, the function is given by fx where x tending to infinity, or x is very big number. So before that, we considering the limit of a function at the x tending to infinity, we should take a look at the rate of a growth for some function, and this is the order of rates of a growth for some function that we can consider. It means that it started from the constant function, then logarithmic function, then the polynomial x to the power of n, then exponential function, and at the end is x to the power of x. Let us take a look at the situation by sketching the graph of this function in the aid of Desmos program. So over here we have the constant function. That red function determine the constant function. It could be negative or positive, or it could be a big number. However, if I just compare this situation by the logarithmic function, the logarithmic function has a greater actually rate at the end of the day later. However, it it's too late, but at the infinity the value of logarithmic function overwhelm this constant function. Let us consider the ln function. As you can see over here, it's smaller than the constant function at the beginning, but as much as you go forward and going to the infinity, as you can see, that blue graph overwhelmed the red one. However, if that red one becomes bigger and bigger as a constant function, but at the end of the day, when you go too much to the infinity, means that at somehow the value of 100,000 or more than that one, the blue graph will overwhelm that value, and you can see that the rate of growth for that type of the logarithmic function is bigger than the constant function at the end of the day. So more than that one is a polynomial function. However, you consider the linear equation or x squared, or even if you just make the bigger exponent over there. For example, if I have x to the power of 4, as you can see, the actually rate of a growth for this case is bigger than logarithmic function, means that it's going to infinity at the beginning, not up to the end. If I just take a look at the value at the infinity, as you can see, it's too big, and the value over here for the polynomial function is bigger than the logarithmic function. And the another one is a exponential function. Even for x4, you can see that at this point, means that at the point 1.42961, which is the value of e, the value of the exponential function overwhelm the value of the polynomial, and it's bigger than that one, means that the rate of exponential function, as you can see, is bigger than the rate of that polynomial function. And x to the power of x is a bigger one, means that the biggest rate belongs to the x to the power of x. As you can see, when you're tending to infinity, that value is too big, and it's bigger than the exponential function as well. So by knowing the rate of a growth over here, you can calculate the limit at infinity. This limit is important because it can determine the attitude of the function at the infinity, and this helps us to know their asymptotic at the infinity, means that for this type of the function, it's determine the value at the infinity, or the asymptotic attitude of the function at the infinity will determine by evaluating that type of the limit. When we want to sketch the function, it's too important to know that type of the limit. For example, at the beginning we have a number constant over x, and as you can see, the constant is at the beginning, and x is a type of a polynomial which has a bigger growth over there. So the number over infinity means that we have the constant value that we divided with the big values, so the results will be 0. Always if we divide one function with the lower rate of a growth over the greater rate of a growth function, then the result will be equal to 0. In the next case, we have a function that the rate of a growth at the numerator and denominator are the same. To evaluate that function, we should divide the terms by the biggest growth that you can find it over there. Means that to calculate that one, let us tend x to infinity, then divide everything by x squared. The first term by x squared is 5, so the second one will be minus 3 over x if you divide it by x squared. The next one is 1 over x squared, so you should divide the 1 or constant by the x squared. For the numerator value, denominator value as well, if you divide it by x squared, we have 1 and 1 plus 1 over x squared. And as you can see, all of these terms means that the constant over x tending to 0, this constant over infinity tending to 0, and this one, and at the end of the day the value of that limit is equal to 5. So for the next one we do the same thing, means that we should divide that terms by the biggest growth, and then you will reach to the situation of number over 0 which is equal to infinity, means that over here the rate of a a growth for the numerator is bigger than the denominator, and if you divide it by x even, then you have 3x plus 1 over 1. If you divide it by x, everything that we have it, and we have 1 plus 1 over x, and this 1 over x tending to 0, so we have the infinity over a number when x tending to infinity. If you just substitute the infinity over there, we have a big value at the numerator, however we have a number at the denominator, and the result should be equal to infinity. The most difficult case that you can consider it is a third case that we have it there. And if you take a look over here, and if you remember that we said that the roots, the m roots of x to the power of n is as the same as the fractional exponent, means that we can rewrite that one as a x to the power of n over the roots, which is m, means that we can rewrite that one like this. So over here, by dividing everything by x cubed, then we will have the following expression, means that we have the limit of let me just rewrite it over here, x tending to infinity, and let us divide everything by x cubed over here. If I divide everything by x cubed over here, 6x cubed over x cubed will be 6, and then we have minus 1 over x squared, which tending to 0 at the end of the day. And dividing these terms by x cubed means that under the roots I should divide it by x to the power of 9, because x cubed, as you can see, x cubed can be written as x to the power of 9 with the third roots of or cube roots of x to the power of 9 is as the same as x cubed. So 9 over 3 is equal to 3. So I should divide the terms under the roots by x to the power of 9 to do the same thing. Means that the third root remains over here. We have minus 7 x to the power of 9 over x to the power of 9 will be 1, and we have 3 over x to the power of 8. So over here, as you can see, the value that we have it there means that 1 over x squared tending to 0 and 3 over x to the power of 8 also tending to 0. The remaining things at the end of the day will be 6 at the numerator, and at the denominator will be the third roots of 7. Third roots of minus 7 indeed. So if we have the odd number as a root, it's allowed to have a negative number under the root, otherwise you cannot have the negative value. So let us take a look at the situation when we have a graph of this function. As you can see over here, I sketched that function which is 6x cubed minus x over minus 7x to the power of 9 plus 3x to the power of 1 over 3, or the third roots of that one. And with this situation you can see that the y equal to 6 over minus 7 to the power of 1 over 3, or third cube of minus 7, determine the line that the function tends to that value at the end of the day when we tending to infinity. Means that at the right side and left side of that value is they are too close to each other. So if I just change the value of that one to the plus sign, then that function also will be plus, and we have this situation. And again, the value tending to 6 over third roots of 7. Let us examine the even roots. Means that I will change that one to 2, but at the denominator I divide it by 4, and I change the function to the 8. And the result, I mean the asymptotic property, should be 6 over the fourth root of 7. Let me just make it as a fourth, and as you can see, at the infinity is tending to the same value. Means that it will be this terms as a limit of the function when we tending to infinity, to the plus infinity and minus infinity as well. And it's a roots over there. But if I change it to the negative sign, as you can see, we cannot determine this value. As you can see, it's undefined, because because minus 7 under the fourth root cannot be determined, and the function over there also tending to infinity at the beginning, because minus 7x to the power of 8 under the roots make the negative values, and it cannot be that much big. So if it's big, then the value under the even roots will be negative and it will be undefined. So this is the case over here. As a last example for this form, let us consider the limit of the following function, and as you can see at the denominator we have the exponential function, and we said that the rate of the exponential function is bigger than the polynomial, so the result should be 0. We can see this case also at the graph of a function. So as you can see in a graph of a function, when we have exponential function at the denominator, the value of the function and infinity tending to 0. So if I remove that e to the power of x, as you can see, the value that we have it is tending to infinity like that, because we have some polynomial function. But if we divide that one by exponential function, then the attitude of this function is changed and it's tending to 0 at the infinity, plus infinity. You should care about the sign of x here. If I put the minus x, for sure at the plus infinity the value of the function tending to actually infinity as well. What does it mean? Let us take a look over here. If I just put that x tending to minus infinity instead of x tending to infinity, if I just change that x to minus infinity, then the situation of this function is totally changed, because when we have the negative exponent of e to the power of x, you remember that e to the power of minus x, or negative value for x, should be written as 1 over e to the power of x, means that that value will be inversed. And in this case I can rewrite this expression as follow, means that I can rewrite that one as a limit of e to the power of minus x. I just put it at the numerator right now, times x to the power of 7 and plus 3x squared plus 1. And over here right now, where you just take a look on it, as x tending to minus infinity, then the attitude of this function will be changed. These terms will be calculated in a denominator right now, and these terms e to the power of minus x should be calculated at the numerator with the positive exponent, and the value of this limit becomes plus infinity. It's not equal to 0 anymore. So after that we discuss about the limit at infinity, it's necessary to talk about the squeeze theorem as well. So at this point let us take a look at the squeeze theorem. The squeeze theorem said that if you have three functions like f of x, g of x and h of x, that I just sketched the graph of them, and one function as f of x in neighbors of a, here is a neighbor of a, it's sandwich between these two functions, it's a squeeze between these two functions, means that the f of x is in the middle of h of x and g of x. As you can see, h of x is at the bottom, f of x is in the middle, and g of x is at the top or over all of them. It looks like that you make a cheese sandwich, that the cheese is f of x and the bread is given by g of x and h of x. If f of x is a squeeze between these two functions in a neighbor of a, and also the limit of these two functions means that g of x and h of x at the side of this function is tending to L, then the mid function also has the same limit, or the function fx has a limit of L as well. The best example in this case is the sine limit of sine x over x, where x tending to infinity. We know that the sine x is a value between 1 and minus 1, and if I divide it by x, then I reach to this value. And over here, if I tend x to infinity, if I tend x to the plus infinity, as you can see, the value of 1 over x tending to 0 because it's 1 over infinity, and value of minus 1 over x also tending to 0, and because of that the value in the middle, or sine x over x, also should tending to 0 as well. Care about it that the x tending to infinity, not tending to 0. Another example is evaluating the same limit where sine x over x, where we have the limit of sine x over x, where the x tending to 0. There is one inequality that you can prove it, but it's not a place that we can prove it over here. It's need a lot of information in a trigonometric function and also the algebraic expression. So just accept that where sine x over x is calculated and x tending to 0, the value of this limit is equal to 1. We need this type of the limit too much later on to calculate a lot of limits based on that things. It's not a bad idea to take a look at the behavior of this function as well. So again, we return back to the Desmos. This is the form of a sine function. It's fluctuated or alternated, oscillated up to the infinity like this. And you can consider the value of y equal to 1 and y equal to minus 1. As you can see, the value of sine x is restricted between the value of 1 and minus 1. And for the value of actually pi over 2 or 1.62, the function is given over here as 1, and as you can see, it's coming down over here to just fluctuated over this curve. Right now, let us consider the sine x over x as well. The function of sine x over x, as you can see, at the origin is tending to 0. You can see that it's tending from a right side and left side to the value of 0. But at the infinity, if you just take a look on it, at the infinity, the value of the function tending to 0. Let me just put 0 to see that what is the attitude of this function at the point 0. This one is twisted through the horizontal line, and at the end of the day, when x tending to infinity, the function tending to 0 over there. So by knowing this fact that the sine x over x tending to 1 at the origin, means that at here where x tending to 0, of course at the point 0 it's undefined because the denominator is 0, but when it's tending to 0, the value of the function tending to 1, as you can see, is too close to 1. When we have minus 0.05, the value is 0.99958, and it's too close to 1, and at the end it's tending to 1. So let us calculate some limit based on this fact as well. So we have this type of the limit over here that we want to calculate it. First of all, limit of sine of 3x over 5x, where x tending to 0. I emphasize that the x tending to 0. If x tending to infinity, the result will be 0, the result of this limit. But if x tending to 0, you should use the fact that the sine of x over x is equal to 1, limit of that one indeed. So we will rewrite that one as a limit of x tending to 0, since we know that the limit of sine of u over u, where u tending to 0 is equal to 1, we try to construct that terms, means that we will write that one as a sine of 3x. So we have sine of 3x at the numerator. At the denominator, we need to have 3x to have the limit equal to 1. But if I multiply it by 3, we should divide that one by 3 as well, means that we should construct 5 at the denominator. For this reason, I just write 3 at the numerator. Right now, this 3 and this 3 at the denominator can be cancelled, and also I will put 5 over here. Then the result of this expression and the previous one is as the same, with one difference is that this part of this limit is tending to 1. So this part is tending to 1. Right now we have 3 over 5, so the result will be 3 over 5 at the end. But we have also one equivalency over here, that the sine of u, tangent of u, and u, all of these three functions has the same behavior, where u tends towards 0, to origin. So where u tending to 0, then sine of u, tangent of u, and the u by itself has the same attitude. Means that from very beginning, instead of calculating like that, we can rewrite that one as a 3x, because the attitude of sine of x and 3x is as the same over 5x. And right now, by cancelling the x, you will reach to the result, which is 3 over 5. This is the short way to calculate that type of the limit. For the second case, again, we have the similar situation. Means that we have limit, and again, tangent square can be written as a sine square. So I will write that one as a sine square of 3x over cosine square of 3x. So I can write the tangent like this, cosine square of 3x as well, cosine square of 3x. This one will be the tangent square, and it's multiplied by 5x square. So of course x tending to 0. You shouldn't forget to put that actually terms at the bottom of the limit. So right now I can again split them. What do I mean by the splitting? Means that I can rewrite it as follow: limit of x tending to 0, and for that case I can rewrite that one as sine of 3x. So to make that terms, I need the 3x at the bottom as well. So I will write the 3x at the bottom, and I square the total expression. Right now I have sine square of 3x, and because I wrote 3x at the bottom and it's a square it, I should put 9x square over here to avoid the problem of having some non-equal expressions. So again, we have the similar things that we had it previously. I mean, this part, the denominator is not changed, and I should put it over here right now. So at the end of the day, as you can see, this part is tending to 1. This part is tending to 1. And this x square and this x square at the denominator will be cancelled. The cosine of 0 is equal to 1. So this one also tending to the value 1. And the remaining part is 9 over 5. 9 over 5. So the limit of that expression is 9 over 5. However, at the beginning of that calculation, because tangent is equivalent by u, instead of that case I could write 3x totally a square. This is the numerator, and for the denominator I can write 5x square, and 3x square, 3x totally a square is as the same as 9x square over 5x square. And after cancelling the value of x square from both sides, numerator and denominator, the result will be 9 over 5 as we found it at that case as well. So this is the case that we have it for the limit of sine and tangent and x as well, where x tending to the point 0. Let us take a look at our diagram again. So in our diagram we had the infinity over infinity as well, that we discussed about it at the limit at the infinity. We had 0 over 0 that we discussed it previously. We had the number over 0 that it's equal to the infinity, and based on the sign of the 0 we can decide about it, and the infinity over the number over infinity is equal to 0. And also we had that case of sine x over x that we used the squeeze theorem. And for the exponential cases like 1 to the power of infinity, 0 to the power of 0, or 0 to the power of infinity, we should use the property of exponential and logarithm function. But we need also to know the Hospital rule, because at the end of the day it's changed to the form of infinity over infinity or 0 over 0. That cannot be solved with the method that we learned it up to here. So we just skip from that concept, and as a part of the application of a derivative we will discuss about that things as well when we have the derivative, and the discussion of a derivative will be done. So I just finish our lecture at this this point, and later on at the next lecture we will discuss about the continuous function, and we will solve some example about that things as well. Thank you for your attention.